Hey, what's up YouTube? It's BeetlePlayer1011 here. Today we'll be talking about continuity in our next installment of single variable calculus. So, what is continuity? Continuity is, in the simplest way possible, when a graph is going over some interval and it doesn't stop. So every single variable on an interval has some value in that function. So I'm going to take a look at this section right here. On this interval, it's continuous, and how would you know if it's continuous? Basically, you should be able to draw it without picking up your pencil. And as you can see here, I can draw it without picking up my pencil. Discontinuity is when you basically have to pick up your pencil. So I go here, and then I pick up my pencil, and then continue drawing over here. This over here is a discontinuity. And we'll be going over the types now, but let's get into the mathematical definition of what continuity is. There are three conditions to having a continuous function at some point c. First is that f of c must exist. So f of c exists. What that means is that the function at some point c has to have a value. Here, for example, at this point, there's a circle dot that's not filled in. That means at this point, f of c does not exist. At this point, f of c does not exist either. However, at this point, let's say f of c does exist. The second condition is that the limit as x approaches c exists. So what this means is that it approaches some value. Now you may be asking, well, isn't that the same thing as number one? Well, no, because the limit is not just plugging in the number, if you remember. The limit is when you approach it from the left and approach it from the right. So let's look at this case number 2. As you approach it from the left and you approach it from the right, you get infinitely close, but never exactly there. You approach this one value, so the limit does exist. However, the first condition isn't met, so it is not continuous. However, the limit does exist. There's also a point here where f of c does exist at number 1, but it's discontinuous because the limit does not exist. F of c exists. At this point, this is the value, but if you take the limit, as you approach it from the left, it actually approaches this value over here, but if you approach it from the right, it approaches a different value, so the limit does not exist. As you can see, both of these conditions are essential. Now, the final condition is that f of c is equal to the limit as x approaches c. Now, the graph to the right doesn't exactly explain why this is necessary, but it should be, I'll draw it in a second now. So, let's take an example where you look at case number 2, and let's say we just give it a value over here. Hold on, it should be orange. Let's give it a value over here. Now the first two conditions are met. F of c exists, and the limit as x approaches c exists. Both of those conditions are met, but number 3 is not being met, because the limit and then f of c are both different values, one here, one here. So all three conditions are necessary for it to be a continuous function. Now let's go over the three types of discontinuity that you'll recognize here. The first one is called a jump discontinuity. So a jump discontinuity is when the value exists, but the limit does not exist. So as you can see here, the limit does not exist, but the value exists over here. So what's going to happen is that it's going to jump from this value to this value. That should be self-explanatory as to why it's jump. The next one is a little bit more complicated. This one is called removable discontinuity. So I'm just going to call it removable. Removable discontinuity has two different types, but both of them are very similar, so I'm going to use number 2 as the example. As you can see, it's color-coded. This is removable discontinuity. The limit exists, but the value either does not exist or it's at a different place. So as you can see here, it approaches this number, but this point is removed here. The point, the f of c, is removed either to a different place or it just simply is not there. The last type is an infinite discontinuity, and that's case number 3. So infinite discontinuity is basically when you see a rational function and it approaches infinity, the limit does not exist. So obviously, I spelled infinite wrong. Sorry. So the limit does not exist, and neither does the value. It's all in all very discontinuous. One goes down, one goes up. The limit does not exist, the value does not exist. So those are your three types of discontinuity. Now let's go on to functions and giving you examples of continuous functions and discontinuous functions. So a polynomial function is continuous everywhere. As you can see, every point on the function has a value somewhere. Now let's go to a rational function. A rational function is continuous everywhere that's in its domain. Basically, it's continuous whenever its denominator does not equal 0. So when the denominator equals 0, you get this infinite discontinuity. Now let's look at the absolute value. That is also continuous everywhere. There's this corner here, but it exists, and the limit approaching it also exists, so it's continuous everywhere. Trigonometric functions are continuous in its domain, meaning that for like sine, for example, it's continuous everywhere. For tangent, it has infinite discontinuities at every pi interval. Remember, the interval for tangent, this is a tangent function, is pi. So at every pi, there's a discontinuity called infinite discontinuity. Now let's look at exponential. Oh, also another trig function, for example, that does not have a remember, this is similar to the rational function. Here, for the trigonometric tangent function, when cosine of x equals 0, tangent of x is a discontinuity because tangent is sine over cosine. For example, let's say sine x over x. That has a removable discontinuity. I'm just going to draw it up here for a second. We went over the limit, but it is a removable discontinuity. What it looks like is this. So sine x over x looks like that. And there's a removable discontinuity at x equals 0 because the denominator is x, but the limit does exist. However, it's still discontinuous at that point. Exponential, this is, for example, e to the x. This is continuous everywhere. The log is continuous in its domain, so basically whenever it's positive, you can't take a log of a negative number. Radical, you can't take a radical of a negative number, so it's continuous in its domain where x is greater than 0. Now, the greatest integer function is an example of a jump discontinuity. It's discontinuous at every integer. At, for example, x equals 1. The greatest integer at x equals 1 is 1, but the limit does not exist because at 0.9999, the greatest integer is 0, but at 1.0001, the greatest integer is 1. So it's a jump discontinuity. The limit does not exist, but the value does. So those are examples of functions and their continuity. Now let's go over three important theorems. The extreme value theorem. So I'm going to draw a graph over here to demonstrate what the extreme value theorem is. Now, truth be told, I made a stupid mistake when I took the AP Calculus BC exam, and I actually got this wrong, and it was one of the easiest questions on the test. So, know these theorems because some of the questions on your AP test will literally just be, what is the extreme value theorem? And it should be a free point that I did not take advantage of. Just personally, if you're curious, I did get a 5 on it because I did well on the other parts, just not this one question, sadly. Anyway, so I'm going to draw a function over here, like this. Now, the extreme value theorem says on a given interval, I'm going to take these two intervals, a function achieves a maximum and a minimum. So, when I have an interval here, it'll achieve a maximum and minimum somewhere, and a lot of the time, it'll just be the endpoints. In this point, the maximum value is actually over here. If you see, it rises a little bit, although I did just sketch this, so yeah. So there's a maximum. The minimum is down here at the other endpoint. So even if it's at the endpoints, right, even if it's just decreasing the entire time, there will still be a point where there's a maximum and a minimum. The intermediate value theorem says that on a given interval, a to b, so let's do this, a and b, there is a given value c in between a and b that has a value in between f of a and f of b. So let's sketch this out. This is f of a. As you can see, it goes down here. and then f of a is this value. F of b is here, so f of b should be over here. This theorem says that there is some value c, we don't know what, that has a value that's in between f of a and f of b. So c is in between a and b, and then f of c should be, and it is, between f of a and f of b. That is the intermediate value theorem. The continuous function theorem says that when we take this function f of x, we can do a few things to it that would still make it a continuous function. First, we could just multiply it by something, k times f of x. All this will do will make it stretch out or squeeze a little bit depending on what you do, but it'll still remain a continuous function. 2, you could do whatever functions you want to it with g of x. So I'm just going to write g of x here. If g of x is a continuous function, what you can do is you can add them, and all you're going to do is you're going to shift these points a little bit. It'll still be continuous. You could subtract them, same thing. Multiply them, same thing. And it's like multiplying polynomials. You get another polynomial. Or you could divide them. And when you divide them, there's a caveat. G of x cannot equal 0. So remember, when you divide two polynomials, what you'll get is a function that looks like this. So it's still continuous on every point, but it has an infinite discontinuity where the denominator g of x equals 0. And that's continuous function theorem. Now, I hope you enjoyed this video. If you learned something, remember to give it a thumbs up and subscribe, and I'll see you tomorrow.